Welcome to the Boston Echo Board's review course. In this sneak peek of a sample concept, we will be going over the principles of color flow Doppler examination and break down this complex process into its component parts. I hope you enjoy this sneak peek and stay tuned for the online launch of the Boston Echo Board's review course. One of the most important concepts to appreciate to understand the principles of color flow Doppler is the concept of phase shift. This shift is indicative of the motion of an RBC from one ultrasound pulse to another, and the distance that RBC travels over time is directly proportional to the velocity and hence the Doppler shift. For example, if a transducer is interrogating this red blood cell, a pulse is sent out which gives information about the position of an RBC. The RBC moves away from the transducer, another pulse is sent out to interrogate the position of the RBC at the next, with the next pulse. Now, the amount of shift between these two pulses, how much out of sync they are with each other, is proportional to the RBC velocity and hence the Doppler shift. And this is called the concept of phase shift. And these pulse pairs, which means one pulse at one location and the second pulse at second location, these pulse pairs are analyzed for each pixel, and the total number of pulses are called color packets that happens within the region of the color flow Doppler box. Now, the final calculated velocity at a specific pixel is the average of calculated velocities. Now, this seems like a pretty complicated concept, but we'll go over that in about a second or so. We're all familiar with this color flow Doppler box that we place on valves to assess for the severity of regurgitation. Now, let's go over the anatomy of a color box in a greater detail. If you look at it in a little bit more zoomed fashion, you will be able to recognize that it consists of multiple scan lines. And if you look and even zoom on these scan lines even more, you'll realize that each scan line is much thicker than what it seems to be and consists of multiple small square-like boxes, rectangular boxes referred to as color packets. And when you look at the color packet, there is something a little bit more complicated going on, and that is the assessment of the velocities of RBCs at different locations and the comparison and analysis of these phase shifts between these pulse pairs. Now, I'll go to this animation. It will happen a little fast, and then we'll break down this animation by step to see what happens during a phase shift analysis in a specific color packet. Now, let's zoom on this color box from a distance and see what happens. As you can see, keep going close to the color scan line. It consists of multiple color packets. When you open up a color packet, there's a little bit more stuff going on in there. As you can see in this situation, the location of RBC, analysis of its position, whether it's moving away or towards the transducer is being analyzed, and the position of these two RBCs is compared for the time it takes for these two RBCs to move either away or towards the transducer. Now, this happened pretty fast. That is, the two pulses of 1 and 2 are being analyzed for phase shifts, and the average velocity variance, and magnitude is calculated instantaneously. Now, let's break down this complicated process in a stepwise algorithmic fashion. So now we are looking at the same color packet, but in greater detail, and we will break down this process in an algorithmic fashion to really understand the concept of phase shift. So now we're looking at two RBCs, RBC A at location 1 and RBC B at location 4. And we have this ultrasound transducer which is interrogating by sending out the pulses to establish their current position and the direction in which they are moving. For example, it sends out a pulse to RBC A and establishes the go-return time and the distance the RBC is from the transducer. Now, RBC A travels from location 1 to location 2. Another pulse is sent out to location 2 and establishes the distance and the time it takes to travel to location 2. Now, the go-return time for pulse 1 from position 1 to position 2 is longer for RBC A. Now let's look at RBC B that is present at location 4. A pulse is sent out to establish its current location and the distance from the transducer, and the second pulse establishes while it is moving from location 4 to location 3, the distance it has traveled and the time it took for this RBC, that is RBC B, to travel from location 4 to location 3. Let's just call the first one as pulse 1, that's a pulse pair of pulse 1, and the second one as pulse 2, this is the second pulse pair. Now the comparison of the go return time for RBC A from position 1 to 2 is longer, and the go return time for RBC B from position 4 to position 3 is shorter. And the delta time it takes, the difference in time between these two pulses, is the velocity of the RBC and is also proportional to the Doppler shift. Now that is the concept of phase shift, which analyzes the position of RBC either moving towards or away from the transducer. And now we will assess how this time is calculated into a Doppler shift. So let's look at this thing in a greater detail. As this animation is happening, you can see that RBC A is moving from location T1 to T2, and look, RBC B is moving from location T1 to T2 also. Now, if you look at it a little bit closely and ignore this animation, you see that the go return time from position 1 to position 2 for RBC A is longer, whereas the go return time for RBC B for position 2 to T1 is shorter. So the distance that the RBCs have traveled either away from the transducer or towards the transducer is proportional to the velocity, or the velocity is proportional to the total distance they've traveled. So these are two pulse pairs that are being analyzed for phase shift, which means how much out of sync or in sync they are. So multiple pulse pairs are recognized and analyzed in a color flow box and in individual color packets. And the average velocity of the whole color box is based on the averaging of all these color packets, which means if majority of the RBC are moving towards the transducer, it'll show up as red. And if they're moving away from the transducer, they're going to show up as blue. So the average of all these color packets comes out as the average direction of blood flow either towards or away from the transducer. Now analyze a third RBC over here, which we didn't go over in the first time, and that's this RBC that ain't moving in either direction towards or away from the transducer, and therefore the delta time for this RBC is 0, which means it is neither moving away or towards the transducer, and this will demonstrate as a 0 Doppler shift. So which means it could be moving side to side, not away from the transducer, and therefore the concept of having no flow is not correct. It just implies that there's no Doppler shift. There's no if the pulse pair analysis of this specific RBC demonstrates no delta time, which means it's neither moving towards or away from the transducer, hence the black line in the middle of the color flow box. Therefore, a color flow Doppler region of interest that we apply during echocardiography consists of multiple scan lines, and each scan line has hundreds of these color packets, and each one of these color packets, RBCs are being analyzed either moving away or towards the transducer based on phase shifts of the individual motion. And if you go further on this thing, you will recognize that each scan line has all of these color packets, and when you go into greater detail on these color packets, you see how the phase shift is analyzed, which means how different the pulses are from pulse 1 to pulse 2 in the analysis of a motion of RBC towards or away from the transducer, and the delta time between pulses determines the velocity, the distance, and therefore the Doppler shift. And that's the principle of color flow Doppler. So in this final review, we'll put together the concepts of phase shift and color packets with that of a velocity profile that we see and use during routine echocardiography. As you can see, that this blue line corresponds to this RBC that is moving away from the transducer, and the red portion corresponds to the RBC that is moving towards the transducer. Now, important thing to appreciate is that the speed or velocity and the distance that it covers is represented on this scale, which means the faster it moves and the more it moves, the more it will be towards the edge of the velocity. And if the speed and the distance covered is more than what the transducer can assess, or is more than the pulse repetition frequency, it will be aliased. The important concept is to recognize this black bar, which is represented by this green RBC that is at position C, which is neither moving away or towards the transducer, but could as easily be static, or moving in a direction which is completely orthogonal, which means the delta t for this time, the delta t for this RBC C is 0. And it could be moving in any speed or any velocity for as much distance, but it would not be gained, would not be analyzed, and would not have any delta t to demonstrate a Doppler shift, and hence this RBC would be seen as the black portion, which means there's zero Doppler shift, and it does not signify that there's no Doppler, there's no flow. It just implies that it cannot assess the delta t for this RBC, that it is the go return time remains the same for the pulses that are sent to analyze RBC. And the only way this can be seen as positive or negative is when it moves away or towards the transducer. So therefore, black portion, which is this portion of the color flow scale, implies a zero Doppler shift and not zero flow.